here to see me talk about this concept of IMTA. I can't recall whether Dennis explained what IMTA is, but IMTA is an acronym that actually stands for Integrated Multi-Trophic Aquaculture. So it's a type of aquaculture system, as you will see, that integrates multiple species into an overall system to improve efficiency. So before I really get rolling on this, I want to really introduce not only my co-authors who have already been introduced, but also the team of people who have worked on this project. This is a project that required a lot of expertise and a lot of talent, and you can see from the list we definitely have that in the group that has participated. So not just scientists, but also students, interns, and technical staff. It's been a wonderful project because of the interaction that we've had with this group. And I also want to mention the Specialty License Plate substantially has funded this project. We've had other funding from, especially for our interns, et cetera, from the Link Foundation, Sea Grant program, and some USDA, and also some funding for some of the particular portions of the project from a company called Florida Organic Aquaculture, which does shrimp culture out here in Fellsmere. So, I get started. How many of you eat seafood? A lot of hands, even more than in the earlier lecture. There's a lot of people eating seafood now, a lot more. When I first did this lecture in 2013, I'd say there was half as many people raise their hands so that they eat seafood. If I was to go into the Midwest, where us people from Illinois are, I would get even fewer hands. Maybe 2 or 3 in a crowd like this would raise their hand. But if we look at the United States overall, Americans eat about 14.6 pounds per capita, per person, per year of seafood. If you look at the world as a total, we eat a bit less than half of what the rest of the world eats on average. Now, that doesn't mean that everybody in the United States only eats 14. There's people that eat none, and then when you get to the coastal areas like here, people eat probably closer to that 30 pounds per person per year. So, but the worldwide average is about 35 pounds. U.S. imports 90% of the seafood we consume. It leads to about a $14 billion trade deficit. 50% of the seafood we're eating today comes from aquaculture. To me, this is a success story. This is part of the success story, and you'll see why as I go on and show you some of the data. Global aquaculture today is about a $130 billion industry. People think of it as just a small startup kind of industry. A $130 billion industry is a big industry. In the United States, it's a $1.4 billion industry, which is only about 1% of the total world production. So the United States is lagging behind substantially. The component that's just in Florida, it's a $78 million industry. It was up to about $100 million just a few years ago, but there's been a curtailing in that a lot due to reduction in production in the clam industry. So, how does fish compare with our other meat products? Well, we have chicken at the top. We consume a lot of chicken. This is data from 2003. It's based on availability of products. So you can't actually see how much people put in their mouths, but we know what the availability is. Beef is up there, and then our seafood falls right down here, about 14.6, so just under turkeys and the consumption. So those turkeys, that's the turkey that you eat on a roll or at Thanksgiving, right? That's their prime time for being sold is Thanksgiving. On a worldwide scale, if you look at production of seafood or fish versus beef, this past year, production of fish in aquaculture actually surpassed worldwide production of beef. So we think of beef as a huge meat or protein production industry, but it's actually fish is actually number 2 below chicken nowadays. So it goes from a worldwide perspective, it's chicken, fish, beef, pork. If you go and look at what the breakdown of that 14.6 pounds is, we'll see that shrimp is number 1 at the top, followed by salmon, and then tuna. And this tuna, incidentally, is canned tuna for the most part. followed by tilapia, pollock, and the Pangasius catfish, and then there's our catfish here. If you look at this, I've got some of them in light blue and some in dark blue. The ones that are in light blue are all substantially going to be your aquaculture products in the sale. So there's a lot of aquaculture products that you're all familiar with that are in the stores. Catfish there, when we talk about fish production, is the #1 fish produced, and I'll show you some data on catfish in a little bit. What's at the grocery store? So the point to take on that previous slide is that is sales, total sales. The bulk of that is going to be to restaurants and that sort of thing, about 2/3 of it. When we go to the grocery store, what do we see? These are the #1 group of species that are sold in the grocery store. These are all your aquaculture products. Notice the top 3 I've got listed in aquaculture. Somebody's going to argue with me and say, oh, salmon, that's all wild. Every time I go to the grocery store, it's all marked wild caught salmon, right? 69% of it is actually aquaculture that you're going to see in the store. So maybe there's mislabeling. I'm not accusing anybody. So some more quick facts for you on aquaculture. I've already told you we import about $14.2 billion, giving us that trade deficit. We only export about 4.3, so we still have a substantial export industry. It's just the offset. We have this huge offset. Half of what we export is shrimp. U.S. population now is growing. About 1 new person every 12 seconds, 1 new fish consumer every 12 seconds. We have a global population now that's approaching 7 billion, soon to be 8 billion. So more fish consumers. Nutritionists want us to double our fish consumption. Where is all this fish going to come from, right? That's the question. Well, it could come from our fish stocks. Is it going to come from our fish stocks? No. I'll show you why. This is a breakdown of the status of our fishery stocks right now, global fishery stocks. And you can see here the different pieces of pie. You've got recovering fish. These are stocks that have been depleted and are starting to recover. Those that are still depleted. Those that are currently being overexploited. And those that are fully exploited, meaning if you fish them more, they would become overexploited. Then you've got these other moderately and underexploited. Notice the moderately and underexploited here. The total that we have that is fished at capacity or over is 77% of our fish stocks. So that doesn't bode well for increasing our commercial fisheries. This is a graph of the actual fish production data, and it includes both aquaculture and capture production. All right, so if we look at this, since the 1950s, there was an increase in global fish production primarily from the capture fishery. So you can see here, very little was coming from aquaculture into the 1980s. The problem with the commercial fisheries is after the 1980s, it pretty well leveled off. So you don't see the increase in production, even with the efficient mechanization, et cetera, that we've seen in our commercial fisheries. That's what led to this. But this now is due to the fact that the oceans simply can't produce more. So aquaculture is filling the gap. The gap in demand has to be filled somewhere, and this is where it's going to come from, is aquaculture. This is a graph of growth of aquaculture separated out from that previous graph so that you can kind of get an idea of what it looks like. And you can see since the 1980s, there's been quite a considerable growth. Since the 1970s, it amounts to about 8% per year. Considered to be the #1 growth, agriculture growth industry. So aquaculture is agriculture, incidentally, for those of you who didn't already know that. So let's look at what's happening in the United States. This is 2005, not that long ago in my perspective. Channel catfish industry is king in the United States. Primary fish that we produce is channel catfish. In 2005, it was about 600 million pounds of production, followed by trout, salmon, tilapia, and hybrid striped bass. 2013, which is when we did the last census, there was a census that was missed in between because it was, these censuses are funded by earmarks, or the previous ones were. These are no longer. But you can see between '05 and 2013, the channel catfish industry and the trout industry and the hybrid striped bass, et cetera, have all taken a huge hit in production. Salmon has been dropped on the list so far that they don't even report the data anymore because it could potentially give proprietary data for specific farms. That's why it's a question mark. They have the data, they won't report it because it could give proprietary information for specific farms. So this is not a good story about U.S. aquaculture, unfortunately. We need to do more. And this is concomitant data related to the farms and what's happened with the number of farms. You see, from 2005 to 2013, the number of farms has reduced at almost every sector. Some sectors have shown some growth, but most of them are showing negative growth. So if we're going to be buying local produced aquaculture seafood for sustainability, we need to do more in increasing into the future, increasing our reliance on U.S. produced aquaculture. So what type of fin fish do we produce in the United States? Well, we've talked a lot about food fish. Most people think about food fish, eating fish, but our aquaculture industry also supports bait fish that we fishermen like to have to go out and fish. Ornamental fish. We incidentally have one of the largest inland ornamental fish farms here on site at Harbor Branch called Oceans Reefs and Aquariums. They sustainably produce these ornamental fish in aquaculture systems so that they're not out destroying ecosystems to put pretty fish in somebody's tank. So if you want to buy ornamental fish, buy fish from ORA. The other sector of the fin fish production industry is production of sport fish for stocking. Traditionally, this has been something that's been supported by state and federal fish hatcheries. Nowadays, there's substantial industry in sport fish that's private. In fact, for 5 years prior to coming to Harbor Branch, I was managing a sport fish operation in southern Illinois, producing multitudes, or about 12 or 14 different species, depending on the year, that were being stocked in private fish farms and in public waters as well, on contracts. What are the methods that we use for farming? Well, ponds. Remember, I said catfish was king. I guess it could be queen. I don't need to be sexist. Catfish is the #1 produced aquaculture product, and catfish are produced in ponds, so we see that most of our aquaculture in the United States is taking place in ponds. We have other systems that are used for production of fish. So most of these systems are for fish production. The other systems, like flooded crops, that would be our crawfish production. Bottom culture and off-bottom cultures are oysters and clams, et cetera, for the most part. These are what channel catfish farms look like. If you've ever been to the Mississippi, Arkansas, and that area of the country, Mississippi, Arkansas, Alabama, you would probably have seen, or if you've flown over them, you've probably seen these farms. Very large ponds. These ponds are 10 to 20 acres that they're growing channel catfish in. Trout farms look like this. Trout culture methods are based on the traditional raceway culture that was developed decades ago, many decades, almost a century ago, and used extensively by state and federal hatcheries for trout stocking. Nowadays, it's being applied in a commercial setting, and these are flow-through farms for the most part. They get water from large springs that produce copious amounts of water that flows through the raceways. They're stocked at very high densities, and then the water is discharged. Here at Harbor Branch, we primarily have done work looking at what we call recirculating aquaculture systems, and I'll talk about the specifics of what recirculating aquaculture systems are. But we had a long-term project with USDA ARS for about 10 years. It was about a 10-year project, designing and engineering and making these recirculating systems more efficient, and also developing the husbandry methods for species that would go, warm water marine species that would go into these systems. Quite a nice project. I came in on the project in 2006. It ended in 2010 due to government cutbacks. But we learned quite a bit, and we were making these systems operate quite efficiently. So what are the positive aspects of our recirculating aquaculture systems? One, They allow us to do year-round growth of fish. We have control over the environment. These recirculating system is not a pond system. It can go inside a building, and since you can do that, you can control the heat, you can control the cool, you can control most every aspect. You can control right down to who goes in and out the door. So they're very nice systems from that respect. We can reduce water consumption by doing more and more efficient filtration. We can reduce effluent discharge or control effluent discharge. We can capture that effluent very easily. It's coming out of pipe. Do any post-treatment that we need to do before it goes into whatever discharge or whatever system. It could be landfilled or whatnot. They provide for very intensive production. You apply oxygen in the systems and that sort of thing, and you can get to very high productivity per unit area. They give us enhanced biosecurity. If you control what goes in, what goes out, this is one of the keys to why the chicken industry is so successful, is their ability to do many of these aspects. So most of our chickens are grown in houses, basically, where they control the environment, they control biosecurity, and produce a good, safe food product for consumption. From the perspective of chickens, we don't care too much about escapees, but from the perspective of fish, we do care about escapees. We don't want fish escaping into the environment and breeding, domesticated fish breeding with wild fish. This is the case potentially with sea cage culture. So if we're doing culture in sea cages, then there is a potential. So there have to be higher levels of control in a sea cage culture system that you don't have to have in a recirculating system, because the fish would have to go out of pipe and you have complete control over where that pipe goes. So how does recirculating aquaculture work? From the theoretical perspective, you have a tank with fish, pretty simple. The fish are swimming around in there, you're feeding them. They're doing what fish do, peeing and pooping in the water, and you have to clean that water so that the fish aren't going to die. So the water goes out of the tank through solids filtration. In that solids filtration, we're removing the uneaten feed and feces. And then from there, that clarified water goes into what we call a biofilter. The biofilter is a reactor. It has specialized bacteria. Those bacteria will convert the ammonia that the fish excretes in its urine to nitrite and then ultimately to nitrate, which is relatively non-toxic. And then the water can go back to the fish. At this point, we probably would do more treatment, UV treatment with germicidal lamps to reduce the probability of diseases, add some more oxygen and those sorts of things before it actually goes to the fish. But we are generating waste. We're generating a concentrated sludge here that would have to be treated or manipulated in some way before it could be discharged. We're losing water to evaporation, and we're also losing water to the daily maintenance that we have to do. We're losing water to the sludge. We're losing water when we harvest a crop of fish. So we have to make up water. The general standard is about 5 to 10%. If we only have to make up 5 to 10%, one of these systems is operating pretty well. In our USDA project, we had these systems down to about 3%. So that was very efficient from the perspective of the general standard in science at that point. This is what one of our experimental systems looked like. They were very compact systems. For research, they had multiple tanks, so we could look at different treatment levels of feeds or whatnot, whatever we were looking at from a husbandry perspective. We had solid filtration, and then this is the big biofilter that's cleaning the water. We did multiple species in that project and other projects that we've worked on. We actually did a project in these systems for the FWC with redfish that I don't have listed on here. I should have put that on there. That's a nice species. But we had cobia. We did a lot of work with pompano developing the techniques. So this general system is very adaptable to many different species. We worked with warm water fish, but these systems can be used in cold water systems, et cetera, just by increasing the size of the filtration, make it more efficient under cold water conditions, that sort of thing. So very, very plastic systems from a husbandry perspective. There are limitations. I've made it all sound like rosy, like real rosy so far, but there are limitations to research technology. There are limitations to every technology. Nothing's perfect, right? There are waste products. I already mentioned that. These waste products have to be treated prior to discharge. And treatment means cost to the farmer, basically. That's what it amounts to. If you got to pay somebody to haul it away, or you got to treat it, you're going to pay for that. But it's much easier in a recirculating system. You got one pipe basically running out of a system that has all the waste in it. You don't have to. You're not dealing with diffuse systems. If you're talking about a sea cage situation, you're not going to capture those wastes. They're going out into the natural ecosystem untreated. So on a research system, it is a limitation, but it is one that's technically overcomable. Nobody's ever achieved 100% recirculation. Nobody ever will achieve 100% recirculation in all likelihood, because you're removing water with the product and you have lost evaporation. So people have talked about, oh, we'll cover it, we can recover that evaporation. That's fine. You still got the water going out with the products. And then you have water that's lost through transportation of that sludge away from the system. So, waste. Waste, waste, waste. What are we doing? What are we talking about with this waste? Why are we wasting something in an efficient system? Why are we going to settle for that? Well, we're not. The waste that we're talking about, I've mentioned the uneaten feed and feces, and the liquid excretions, the urine that's in the water that's what we would call our nitrogenous wastes. The characteristics of the waste, they contain a lot of nutrients. Any gardeners out here? Somebody's got to be a gardener. What are some of the things you use for nutrients? These are the nitrogen, phosphorus, there you go. They're all in there. So why are we discharging them? Why don't we use them? That's what the IMTA concept is all about. How do we start in a marine system, start to turn the term waste into resource, so that now we're going to produce alternative products in the system. So go away from a monoculture system to a culture system that has multiple species. And that's where the integrated multi-trophic term comes from. So multi-trophic means eating at different levels, so you have multiple species that are using different sources of nutrient in the system. Very much, and they're integrated. So this is very much an ecosystem, kind of controlled ecosystem concept in aquaculture, rather than being a monoculture system like traditional recirculating. So this system, this is not new. We didn't invent it. But what we're doing is we're moving it inland. Integrated systems like this have been substantially around for centuries, millennia. In China, they've been applying integrated systems for a long time. In Canada, in the last couple of decades, they've been working on a system, an open ocean aquaculture system, to kind of address this aspect that I've already mentioned of open ocean aquaculture, that you can't control the waste coming off the sea cages. So they're working with salmon in net pens, and what they're doing is down current, so you have a prevailing ocean current. Down current, they have raft culture of mussels. Those mussels are catching the particulate matter the suspended particulate matter coming off the cages, eating that, and also eating the algae that's growing because of the nutrients, the microalgae that's growing because of the nutrients in the water between the cage and the rat culture. That clarified water is then going to rope culture of kelp, and that kelp is capturing the nitrogen and phosphorus, growing another product. So now you've got two products off of the same feed that you fed to the fish, 3 products off the same feed. And then down below, they're doing quite a bit of experimentation with how to recapture the settled solids that are going down below the cage. So they're looking at sea cucumbers, sea urchins, and other species that can use those settled solids. So what we did in thinking about the IMTA system is we originally considered a very simple system that would mimic this in a recirculating system. So have a tank, plumb that to something, and then go right back to the tank. Very simple, very easy. It seems like it's easy to apply, fraught with problems. You got to run all that water through every component, maybe way too much for this component, not enough for this component, So we decided early on that concept, although nice, simple, it's probably not going to work in the land-based context. So we went to an alternative design that we developed in our team using what we already knew about recirculating systems. So we took the basis of our system as that recirculating aquaculture system we had developed with our USDA project. We have already had a very high efficiency recirculating system. Let's start to pair that with the other components. So we have a fed culture system with the fish going to our biofilter and solids filtration, allowing us to separate those two resource streams. And then we also incorporated fed culture of shrimp into the system, and for reasons you'll see in a little bit. Now we start drawing loops. So we draw loops off of this central filtration now to other components. Rather than being one big loop, you've got a bunch of individual loops going to each of the separate components, delivering the exact resource stream that component needs with the exact water flow, so you're not flowing too much through and you're only delivering the nutrients they need. And then you've got the final component up here of the macroalgae. And those macroalgae are there to sequester the excess nitrogen and phosphorus, which in a standard research system we would allow to build up to a point, and then that system would have to be flushed and essentially started all over again. So there, another advantage, we control those nitrogen and phosphorus in the system, potentially with that. The nutrients in the system is all driven by the feed that's going into the fed culture components, and now we're producing all these extra crops from the system. So this is what the original schematic design looked like. This is some of the benefits. It's, well, benefit, not benefit, it's complex. So the other design is simple. This design is not simple, but we can control water flow to each of the components. We have much more control over how the components operate. We can tailor the water flow to the husbandry requirements of the species. We can control the water quality. Say we have a species we want to grow that is sensitive to nitrogen and phosphorus. We can pull water coming back from the plants instead of the water in the main loop. That gives us water that's been depleted of nitrogen and phosphorus to grow those sensitive species in. So we have the selectable nutrient flow. If we have a species that needs some sort of specialty filtration, we can add that into the loop and do specialty filtration. Rather than having to filter all of the volume, we only have to filter the volume that's necessary for that species, which means those components can be smaller and less expensive. It's modular, flexible. We want to add another species, add another loop. It's just plumbing at that point. You just run another pipe. Maybe you have to put a little bit bigger pump on there to get the extra flow. The theory is to improve efficiency over the standard recirculating system and if we improve efficiency, we should improve potential profits to a farm that incorporates the design. So this is what the system actually looks like now in operation after 4 years of adding stuff, adding various components. It's been an exciting project. It's been exciting to see the different components grow. And one of the things I want to point out here is we're moving products from here to the others, and I'll talk about that more extensively in a bit. And we've added microalgae culture potentially to the system as well to feed clams and oysters. So one of the aspects of the system that I talked about with research was water conservation, right? Standard recirculating system, remember I said it was 5 to 10%. We were down to 3% in our USDA systems. This IMTA system, the current data, is about 0.5% per day. So we've changed by an order of magnitude the conservation ability of the system by going to this concept, which bodes very well for an inland system. You know, the system, if it's saltwater, you locate it inland, that means you need less salt water. You're less tied to that salt water. So we're pretty happy about that result. When you see the system, you'll see that we have tanks outdoors. So we do get rainwater in the system, and occasionally somebody say, well, you're getting so low because you're getting all that rain. We measure all the rainwater. That 0.5% includes the rainwater. So it's a true number. A problem that we have encountered is heat loss. Remember that, so that water is going, the plants are outdoors. The plants need sun, they're outdoors. The amount of area that's required for plant production is pretty large compared to the system as a whole. So putting a greenhouse is very expensive. We decided to steer away from a greenhouse to look at the harder concept of not having a greenhouse. But that means we have heat loss in the system. So the equation is warm water species plus winter plus flowing water outside equals heat loss. We can't get around it. The pipes have to go out there to the plants. Did some calculations during 2012 based on all of our data up to 2012. And it works out from a BTU standpoint to be equivalent to about 46,000 kilowatt hours if you were heating with electricity, or about 1,700 gallons of propane. So it's pretty substantial heat loss on a yearly basis. That's a yearly basis. So about $5,000 worth of electricity or $3,000 worth of propane. Really would like to recoup those dollars for a farm. So the solution that we're looking at is what we call a full flow heat exchanger to recover the heat before it leaves the building. Easy said, not easy done. Problem is that heat exchangers generally operate off of a high temperature differential. We're operating off a low temperature differential, which means from an efficiency standpoint on the engineering curves, we're at the bad part of the curve, the inefficient part of the curve. But undaunted, we wanted to go ahead and look at this. If we can recover a major or substantial component of that, we're going to save money. So we got a team of undergraduate students from FAU, engineering students, that took this on as a capstone project. We essentially gave them free rein on design, and except that we gave them some criteria, some stringent criteria really from heat exchange design standpoint. We told them it had to be resistant to biofouling or easily cleaned so that we could control biofouling. We said that whatever materials they use, they could leach no toxins into the system. So that means copper's out, some of these other high transfer efficiency metals are out. We told them it had to be inexpensive in construction. That means titanium's out. Titanium would be nice. It's got very high transfer efficiency and it doesn't leach any toxins, but very expensive. In fact, I've got a friend who owns a company that builds titanium heat exchangers, and he ran the calculations, and the heat exchanger for our small prototype system was in excess of $30,000 or $40,000. You start scaling that up to a commercial system, it gets to be cost prohibitive very quickly. The other thing we wanted them to incorporate was automated data collection. So we have a prototype system that they built. It's all plastic. They found some plastics that have heat transfer coefficients that are similar to titanium, a plastic, yes. And they built the prototype design. We had an intern last summer who incorporated it into the IMTA system. That's him installing their prototype. So he took our design, did the CAD drawings to get the perfect, everything exactly installed properly with the automated data collection system. He built the data collection system, and that's what the interface looks like with the data from day before yesterday displayed on it. So very nice system allowing us to start to collect the data. These guys, these undergraduates, you see all the hoses, and they actually did collect data on the system after they built it. So they could do clear water assessments of heat transfer efficiency, et cetera, which is why we know that the heat transfer coefficients of this material is similar to titanium. So now what we're doing is we have it in the system. It's been running in the system now for about 5 months. And in that 5 months, it's gotten quite a good load of biofouling on it. And we want to see what its performance is with biofouling. So that's what's going on right now. This is data from 2 days ago from the system. This is actually 2 minutes worth of data. And you can see the different lines show heat transfer across the incoming line and the outgoing line, or incoming line and outgoing line. And you can see that there is substantial heat transfer going on in the system. So We're pretty excited about the results thus far. The problem is we wanted to do this on a cold winter. Yeah, thank you, Mother Nature. If you want to, the best thing to do to prevent cold weather is to try to do an experiment where you require cold weather, right? So hopefully we do get some cold weather. Because the whole idea with this particular experiment is we wanted to actually adjust the flow and look at transfer efficiency at all different flow rates, and we're not getting enough cold weather to do a lot of cold rates. So hopefully we have another month or two, and hopefully we'll get some more cold fronts. So every time a cold front comes through now, we're quickly going and adjusting flow rates so we can collect that data. So products. Usually when I talk about the IMTA system, I start talking about fish. I love fish. Fish are my product, right? Fish are my life so far. But I'm going to shy away from that for you guys for this particular talk. And I'm going to go into talking about other potential products in the system. Products that are equally important as the fish. So we talked about the assimilative culture. That's the various products that are actually removing nitrogen and phosphorus from the system. Macroalgae is our primary assimilative culture in the IMTA. So this is removing the excess nitrogen from the system that in a traditional research system we would have to discharge by changing water. We are looking at a couple of different macroalgae. This is the area of Dennis's expertise. So he's very carefully chosen the different algae. We've looked at ova, gracilaria, had some hydropuntia in the system for a little bit. These are warm water species that grow very well in warm water. Other species, if we were to move this system to a cold water area, we could do other species. Porphyra. Porphyra is used to make nori. Most of you who like sushi are familiar with nori, I'm sure. It's the sushi wrapper on your sushi, the black algae. Ova is green. Sometimes you'll see a green sushi wrapper or green ova sheets in the store. They're very, very tasty. So that's the one species we're working with as well. That's the primary species we're working with now is ova. We can also do microalgae, phytoplankton, or whatever you want to call it. And we've done quite a bit of work with microalgae as feed for oysters and clams that we've had in the system. I'm not going to present any of that data today, but we've got an extensive database of that. Another macrophyte that we've been working with for a few years, and this work is an add-on that was substantially funded by Florida Organic Aquaculture because they're interested in incorporating the IMTA design in their production out of Fellsmere. So we're looking at methods for producing Salicornia in the system. And I'll show you some pictures of that in a little bit. There's one picture, but I'll show you some other pictures as we go on. So what are some of the uses of macroalgae? Well, from a functional standpoint, nutrient uptake is the use. We want to take up that nitrogen, that phosphorus from the system. But from a production standpoint, it could be used for feed for the herbivores in the system. So we would call this a biotransformation. The nitrogen in the water converted into algae that is then fed to something in the system. And here you've got sea urchins eating it. And you can see they kind of like it. Another potential use is phycocolloids. So agar is a phycocolloid that's used quite a bit in the bio industry for agar plates when you're growing plating or cultures of bacteria. Several of the gracilaria and some other similar species produce that. It can be used for human food as well. Anybody like to eat seaweed here? Anybody? Far fewer than eat fish or seafood in general, but you probably eat a lot of seaweed and don't even know it in your ice cream and that sort of thing. Biofuels is another use for it. Methane, ethanol can be produced from these systems. If you talk to Dennis, though, he'll tell you this is probably a more efficient use for it, is feeding other animals. And then you can use them for specialty fertilizers as well. At the beginning of this study, the approach that Dennis primarily took was to look at some historical data. He's been growing these algae here at Harbor Branch for decades. Has a lot of data to look at, and he's looking at production during those periods to see what what kind of production we could expect here in this area for ulva and gracilaria. This is based on water that was coming from the Indian River Lagoon through our ship channel. This gave us a baseline, crunched those numbers down so he could see what kind of potential production. So he was looking at how we wanted to operate the systems and chose some reasonable, what he felt were reasonable targets to look at to see how we could compare production in the IMTA relative to that baseline. Early on, we were working with both ulva and gracilaria. Both species performed well at high productivity, but gracilaria increasingly became epiphytized, meaning it was having some problems due to contamination with the ulva. And the ulva was very much outperforming gracilaria, particularly due to elevated pHs in the system. So during the daytime, when you have a lot of photosynthesis going on, we would get a pretty high pH in the system, and that wasn't good for the gracilaria apparently. Or it appeared that it wasn't good for the gracilaria, but the ulva loved it. So we continued on with continuous culture of ulva primarily, looking at productivity over the course of several years, doing some manipulations of various things, and found good productivity, and we were seeing improvement over the years as we were getting used to growing this ulva in the system. Got a lot of nice data on productivity based on amount of nitrogen, amount of dry weight per day, but the main thing is that we were showing productivity that was much higher than the baselines that we established from the natural water systems. One of the things we were finding, though, is some problems during the wintertime, fragmentation of the algae, et cetera, that were causing problems. So this past year, Dennis set off on a year-long experiment, looking at aeration. Aeration of the algae is used in order to move that algae, to get algae up into the sun so you can improve light absorption. So the algae that's on the bottom moves up to the top with aeration, gets some sun, then it moves down, and everybody gets sun throughout the day. Facilitates nutrient uptake, reduces diffusion boundary, reduces thermal stratification in the systems, so it's a much more homogeneous culture, so you get more stability. And because it's moving and rubbing against each other, it's going to reduce fouling by diatoms, which are microscopic organisms that'll settle on the thallus. So the light's getting to the actual algae rather than to the diatoms by this natural scrubbing mechanism. So I went through and I did some calculations on total energy requirements for aeration in the system, looking at our pumps, et cetera. And the annual requirement for electricity is about $2,500 a year to aerate the 6 tanks that we have on the system. To me, I'd like to reduce that cost. Remember, I come from a production standpoint, we're always trying to reduce costs. So this experiment was geared towards, one, looking at how aeration affects productivity of the algae, how it affects the plant itself physically, and whether we could reduce the pumping requirement, the aeration requirement. Aeration is done with an air blower. Air blowers require electricity. If we can reduce that requirement, then we can reduce costs. So we set up multiple different treatments, continuous aeration, aeration only during the daylight times, pulsing on an hourly cycle, pulsing on short pulses, and various different short pulses throughout the day to see how that would affect productivity, et cetera. So the results so far, best production is with continuous aeration. In summer, continuous aeration is better when applied only during daylight hours. During the rest of the year, ulva does better with aeration during the daylight only than with continuous aeration. So that means that for 9 months out of the year, we don't have to apply continuous aeration. So when aeration is pulsed during the day, the more aeration, the better, but overproduction is less. So we don't want to go with a pulsed aeration, which would be okay, but we can reduce that aeration and only aerate during the daytime period and maintain good productivity. So a little calculation on that 9-month period where we only have to aerate for part of the day. I'm saying half the day. Comes out to about 8,500 kilowatt hours per year, savings of $930 off that $2,500. Pretty substantial cut in the power bill by that simple manipulation of the aeration, only the aeration. Pretty happy with that result. And coming up in this next year, remember I talked about pH problem with Gracilaria. We really would like to have Gracilaria in the system. There's a lot of nutrients in Gracilaria that aren't in Ulva that some of our animals would really benefit from. So we really like to work out this husbandry question related to pH, et cetera, pH and carbon, inorganic carbon, primarily carbon dioxide, on the growth of Ulva and Gracilaria. So we're setting up a system right now to experimentally look at that in the IMTA system itself. So we're using the same water. It'll be a smaller scale system than these large scale cultures, and then we can really tease out that pH effect. What we're hypothesizing is that more stable pH is going to increase productivity and nutrient removal by the macroalgae and also improve other water quality components in the system while allowing us to start to grow Gracilaria. The other culture, the other macrophyte, not a macroalgae. This is a vascular plant. It doesn't grow underwater. It grows above water. It's found in marshes. In fact, our seed stock came from Volusia County, so it's a local species called Salicornia. It's actually Salicornia bigelovii. It's also got many common names. Samphire is one that's used in Europe quite a bit. In the stores, you'll see it as sea asparagus or sea beans. Traditionally, it's also been called pickleweed or glasswort or saltwort. Glasswort because it's actually a plant that you can burn it and then use it in fine glass making. So it's very interesting plant. So it's a succulent plant. When the shoots are young, before they start to go to flower, they produce a succulent stem that almost has the texture of asparagus. It's where it gets its name, sea asparagus. If you saute that in some olive oil with a little bit of garlic, it produces a really nice dish to go with your pompano that we're growing in your IMTA. This dish actually has, these are all IMTA. So we got the pompano that we're growing in the IMTA, Salicornia grown in the IMTA, and this is actually a seaweed salad made with Ulva. And it's very, very delicious. It's used Oriental or Asian recipe. My aunt made that for me. She came up for dinner. I told her I had pompano. She said she wanted to make this. And so we didn't grow sweet potatoes in the system though. So got to have a starch, right? So the uses for macroalgae, I already talked about human food and showed you human food. But primarily, one of our great interests in using it as feed for herbivores in the system. I'm going to talk to you about that in a little bit more extensively. So I'm going to get into fed culture. I'm not going to talk about fish once again, sorry. But we'll talk about shrimp, and we'll talk about a type of system called biofloc culture. And one of the things we're doing when we're looking at shrimp is comparing biofloc culture to clean water culture. There's some advantages to using clean water over biofloc, but we wanted to see how the two operate in conjunction. First, I'm going to talk also about extractive culture in the system also. So we're going to talk about a little bit about our sea urchin culture. But keep in mind, we've also had sea cucumbers, shrimps, and I'm going to introduce you to a new species at the very end called amphipods. So remember that. So extractive culture, we talked about assimilative culture with plants. Extractive culture we kind of define as the solids removal component. Very fine line in the terminology, but we're talking about solids removal. Initially, we were talking about only solids removal. Now, with the way we've been operating the system, we're also talking about the use of algae and biofloc by other consumers in the system. So doing these bioconversions of the other nutrient products to go into this extractive culture of these other species and to enhance their husbandry. So biofloc, Big story with biofloc in the system. It's becoming very necessary for various reasons. Early on, when we were designing the system and looking at solids in the system, we were thinking we would take the raw solids. We're talking about the uneaten feed and feces coming out, feed it directly to the animals. It would be the easiest way to do it. Get it, feed it to our animals, grow the next crop, and then you're on. Problem is, we were working with sea urchins at the time, and sea urchins didn't like it. Unpalatable. Wouldn't touch it. Big problem. Another problem, when we first started, we presented this idea to, Dennis mentioned the lecture, presented the idea to an audience much like yourselves, and this is the response we got. We're going to eat what? You're going to feed it what? I don't think so. So we went back to the drawing board on that. And biofloc was what eventually came out as the answer to these issues. So we designed what we call an ex situ biofloc reactor. What the biofloc reactor does is it converts that uneaten feed and feces through a bacterial process using beneficial bacteria, much like you convert milk into yogurt. And then that beneficial bacteria is now palatable and to the animals and to the consumer from a consumer acceptance perspective. Most people can understand a bioconversion. These are the same bioconversions that happen in nature. And essentially, coming out of the reactor, it is no longer feces. It is now a bacterial culture. With the feces, we need to do something called flocculation to get it to actually filter from the system. Biofloc is sticky. It essentially will flocculate easily on its own, which means now we don't have to buy flocculation aids in order to get it out. It's much easier to filter. We also looked at the effective incubation time. So our biofloc reactor was designed for about a 2-day resident time, so 2 days of incubation. We actually looked at 2, 3, 5, up to 7 days of incubation time to see how that affected the nutrient levels. In a nutshell, nutrients go down over time. So shorter incubation works out better than longer incubations. This is what biofloc looks like. Very heterogeneous mixture of particles and small animals and bacteria. It's quite a community on its own. So that's what provides the basis for the nutrient profile that's going to be beneficial. The other thing we had to do, since we needed to have these products for other animals, is we started to look at methods for processing them that will allow us to store them and use them in our experiments. So we accomplished that as well. This way we have a source of feed in the long term that we can incorporate into the feeds for other animals. So I'm going to talk about the evolution of some of our shrimp culture questions, and this is data that Susan Larimore is substantially responsible. So the first question that she came up with is that the question of the biofloc itself. So she actually did these studies before we had the prototype designed, while we were designing the prototype. And one of our key questions was, can we use fish waste to support the development of biofloc? So she did a study. Traditionally, biofloc development is supported using carbon sources like molasses, other sugars, alcohol. You know, there's a whole variety. Anything with carbon can be used. Generally, molasses is pretty accessible and is used. So she compared the startup time and growth rates, et cetera, of shrimp that were raised in bioflocs that were started with different levels of fish waste and molasses. Looking at that, she found that biofloc started with the fish waste. We're treating the ammonia and nitrite in the system from the shrimp quite well. In fact, it decreased the time that was necessary to do startup of the biofloc over just using the molasses itself. Quicker startup means quicker stocking time, which means improved efficiency of the system as a whole. All the systems had similar water quality, and they all displayed similar growth. So this was a good result in our quote-unquote guess at using uneaten feed and feces as a resource in our IMTA system. So the answer to the first question is yes, we can do that. The next question is, we've incorporated this into the IMTA. There's the tank and the IMTA system is all around it. Does this system work in a biofloc system if we use it? And can it be maintained by using this ex situ biofloc from this new ex situ biofloc reactor we've designed? We're showing 2 trials. So this is 2 production runs. We've actually completed 4 production runs of shrimp. So stocking and harvesting 4 times under various different conditions of density, et cetera. And what we found is that yes, we can initiate a biofloc very quickly, almost instantaneously. We have a whole reactor full of biofloc. It can essentially go in the tank, and now your startup time is almost nil. And it will support good growth. And I'm going to tell you what, those shrimp taste great coming out of there. I love an experiment where you can eat the results. So, second question answer was yes. Our third question was, how does the bacterial and planktonic composition change in the shrimp biofloc of the IMTA over the course of a production cycle? So this question is looking at what happens with the bacterial communities and the other plankton communities in that biofloc, that heterogeneous mixture of biofloc over time. In bacterial component, she saw variations in counts, total counts over time. Vibrio counts remained constant. The main thing, though, was that there were no enteric bacteria detected. Enteric bacteria would be the baddies, the bad ones that would cause, you get a stomach ache when you eat the shrimp. So none of those were detected. So the system is very much probiotic in controlling that. And then there were effects with the plankton as well, with a shift in the communities, which is not unexpected in communities over the long term. So that was a good result on that question. Question 4 was, can ex situ biofloc from the reactor be used as a protein source in the shrimp diet? Reared in a clear water system. So I'm keeping that distinction. This is a clear water system. Diets were formulated that incorporated different amounts of biofloc as a substitution for the fish meal protein in the diet. And what she found was there was no difference in survival, but growth of the shrimp with biofloc was lower. Seems like it's not a good result, but remember, they aren't dying. They are growing. So it isn't a hugely bad result. So the idea then is, how do we continue to refine that diet to bring the growth rates up with that biofloc potentially? So no difference in survival or growth using dry biofloc in the feed. Question 5, can we use the macroalgae directly, not drying it, anything, just harvest it out of the tank and give it to the shrimp at different levels? So she did different levels of supplementation of ova in the system to see how that affected their growth. And what she found is that she added more and more ova, we saw lower and lower growth. No difference in survival, but she did see lower growth rates with the inclusion of more and more ova. So that means, similar to what I just said with biofloc, good result, it's not killing them. They still are growing, but not at the rate that they could be. Refinement may be required. The next question was, remember I talked about drying that ova and grinding it up. Let's incorporate it into the feed directly rather than giving it as a fresh product. See how that affects it. That's what this experiment was. We found that there was no difference, once again, in survival. But we did see reduced growth rates in the cup studies with smaller shrimp and then larger shrimp in the other studies. So once again, it's not killing them. The ova is not killing them, but we do see reduced growth rates. The question being then with all of these is, will the cost saving of using that cheaper protein offset the longer time to market? So if it does, if you're getting the cost savings by using a less expensive protein, even though you have reduced growth, then it is still a positive result for the system as a whole from an efficiency standpoint. So that's an analysis that we'll have to do on that, maybe. except for this experiment that she just recently ran. This was nice. It was all nice, but this was a very interesting result. And so far she's only analyzed half of this, because this is hot off the presses. She's analyzed the 75-25 replacement, and she still has to analyze her 50-50 replacement. But what she found with the 75%, no difference in growth and no difference in survival. The other thing she did in this experiment, as opposed to the first one, it's in biofloc. It's not in clear water. The shrimp have access to fresh biofloc in the system itself. They'll grow quite well and live in amongst the biofloc. And she was also supplementing with the ova and cutting the ova into different sizes. So one of the thoughts was that larger size that they ran, just tearing it up into big chunks that they did in the first study may not have been, may have made it difficult for the shrimp to eat it. So they cut it in 2 different smaller sizes as well in this study. So cutting it doesn't impact the production, but we didn't see lower growth like we saw in the previous studies. So when we have the biofloc and the ova together, there seems to be some sort of synergistic effect, at least at that 75%. So it'll be exciting to see the results coming out that 50-50 to see if it bears out at that higher inclusion rate. So therefore, we may see reduced costs of the feed in a biofloc system using the ova. Probably not or maybe not in the clear water system. It still needs to be determined, but potentially in the biofloc. We already will see it with this inclusion level. There's already a cost savings there. So very exciting result. This is the new animal we're looking at, the amphipod. The amphipods are a microcrustacean. Some people would call them a shrimp. They're not a shrimp like the white shrimp that you get at the store, but they are a small crustacean. We became introduced to these species because we would see them in and amongst the algae and in some of our other systems. And then one time or a couple of times in between harvest cycles of shrimp, after we would harvest a crop of shrimp, there was a period of time where we were waiting to get a new post-larvae to stock the next run. And these guys would build up in really large mass inside that biofloc tank. We'd leave the biofloc tank running, and they produced large numbers in there. And this is very interesting species. Started to look into it. These are sold in the aquarium industry. You get, for 30 of them, it costs $11. You do the math. I don't know, it may be better odds than the lottery tonight. So we were pretty excited. We want to start looking at this species in a deeper delve. One of the nice things is we're not supplementing their diet with algae or anything like we've had to with the sea urchins and some of the other species, the clams and sea urchins. These guys are living only off the biofloc, growing, reproducing, building up to large biomass. So pretty excited about that. We had one of our summer interns this past summer really take a deep dive into population dynamics under the culture conditions, looked at habitat for the species under culture conditions, found out some really interesting results about their population dynamics that's leading us to new studies and actually to starting to do some experimental level production with one of our industry partners that's interested in this species. So this is a male and that's a female, just in case you were wondering. So pretty happy about that new animal. So when we look at species, we evaluate them based on potential product and ecosystem service. So this guy is doing both, consuming that biofloc as an ecosystem service, which means we can harvest less. We would harvest a product directly that goes to market and produces revenue. And that's some more Salicornia for you. And some funny looking guy in the back.